What if I told you the reason we may never leave the Milky Way isn't because we lack courage, or rockets, or imagination? What if it's the universe itself that has built the bars of the cage? Think about it. The galaxy is 100,000 light years across. Light, the fastest thing allowed by nature, needs 100,000 years just to cross it. And we're stuck playing by the same rules of space and time. No shortcuts, no cosmic loopholes, just physics. So are we explorers in a vast ocean, or fish in a very elegant aquarium? Welcome to the channel, where we don't just learn physics, we wrestle with it. Today we're diving into the deep, uncomfortable laws that might trap humanity inside the Milky Way forever. Stay with me until the end, because this idea only really clicks when you see how the pieces fit together. And if you love clear, curiosity-driven physics that respects your intelligence, subscribe, there's a lot more wonder waiting. Let's start with something that sounds innocent. You're on a train moving very, very fast. Not just fast like a bullet train, I mean absurdly fast. Close to the speed of light. Inside the train, you toss a ball straight up. It goes up, comes down, lands in your hand. Perfectly normal. Now here's the question. Does it behave the same way for someone standing on the platform watching you zoom by? Common sense, the old comfortable kind, says no. If the train is moving and you throw the ball upward, the person on the platform should see it move diagonally. After all, the train is sliding forward while the ball is in the air. And that's true for ordinary speeds, but here's where things get strange. Light doesn't play by those ordinary rules. If you shine a flashlight inside that train, the beam moves forward at the speed of light relative to you. That's not controversial. But the person on the platform watching the train race past also measures that same beam moving at exactly the same speed, not a little faster, not speed of light plus train speed, exactly the same. Now that's weird, because for everything else, balls, airplanes, even sound speeds add. Throw a ball forward in a moving car, and someone standing still sees it moving faster than you do, but light refuses to cooperate. So nature is telling us something uncomfortable. If everyone measures light to move at the same speed no matter how fast they're moving, then something else must give way. And what gives way is time itself. Imagine two lightning bolts striking both ends of the train at the same time, at least simultaneous from the platform's point of view. The observer standing still sees both flashes at once. But the person on the train is moving toward one flash and away from the other. Since light speed is the same for both observers, the flashes don't reach the passenger at the same time. So here's the punchline. Events that are simultaneous for one observer are not simultaneous for another. Simultaneous in an absolute. Now that's not just a philosophical statement. That's physics. It means time is not this universal ticking clock that the whole universe shares. Time is stitched together with space into something deeper. Space-time and motion through space affects how you move through time. And here's where the trap begins. As you go faster and faster, time slows down for you relative to someone else. Lengths contract. Cause and effect stay safe. The universe protects that carefully. But the price is that nothing with mass can ever quite reach the speed of light. Because to do so would require time to stop for you completely. And that would tear apart the logical structure of cause and effect. You see, the speed of light isn't just a speed limit like a highway sign. It's built into the structure of reality. It's the conversion factor between space and time. You can move through space faster, but only at the cost of moving through time differently. And when you follow that logic carefully, patiently, without trying to outsmart it, you discover something profound. The universe isn't preventing us from going faster than light out of spite. It's preserving consistency. The cosmic rulebook is self-consistent, and that consistency traps us. Not with walls, but with geometry. Alright, so suppose we accept the first uncomfortable fact. Nothing with mass can reach the speed of light. Fine. But maybe we can get asterisk close. Asterisk, right? Close should be good enough. 99% of the speed of light. 99.9. Just keep improving the engines. Here's where the second trap closes in. Let's start simple. In everyday life, if you want something to go faster, you push harder. A bicycle goes faster when you pedal harder. A car speeds up when you burn more fuel. The relationship feels reasonable. More energy, more speed. Now imagine pushing a spaceship. At low speeds, it behaves like you expect. You fire the engines, it accelerates. Double the fuel, you get more speed. Everything feels normal. But as you approach the speed of light, something strange happens. The ship still accelerates when you fire the engines, but not in the way you expect. Instead of most of that extra energy turning into more speed, it starts turning into something else, into inertia. into resistance to further acceleration. It's as if the spaceship is getting harder and harder to push. Now here's the subtlety. The ship isn't gaining weight in the ordinary sense. Its mass at rest hasn't changed, but its motion changes how it responds to force. The faster it moves, the more stubborn it becomes. You can picture it like this. Imagine pushing a sled across ice. At low speeds, it glides easily, but suppose magically that the faster it goes, the thicker the ice becomes. The surface stiffens under it. Each extra shove produces less and less increase in speed. That's what nature does near light speed. The deeper reason comes from the structure of space-time. As you go faster, time for you slows down relative to the outside world. That time dilation isn't just a curious side effect. It affects how momentum and energy behave. From the outside perspective, the ship's momentum increases more dramatically than it would under ordinary Newtonian physics. So each additional boost requires disproportionately more energy. Here's the punchline. To reach exactly the speed of light would require infinite energy. Not a lot of energy. Not technologically challenging energy. Infinite. And infinite is not an engineering problem. It's a mathematical impossibility in a finite universe. Think about what that means. Even if you converted the mass of entire planets into pure energy, even if you harnessed stars, even if your propulsion system were perfectly efficient, as long as your ship has mass, even a single atom, you can get closer and closer to light speed, but you can never quite touch it. It's like chasing the horizon. You can approach it endlessly, but it always recedes. And this has a brutal implication for escaping the Milky Way. Our galaxy is about 100,000 light-years across. Even if you travel at 99.999% of light speed, from Earth's perspective, it still takes nearly 100,000 years to cross. Yes, time aboard the ship would pass more slowly. The crew might experience only a fraction of that duration. But the galaxy doesn't care about your onboard clock. The distances remain enormous. And to shave off even a tiny fraction more travel time from the outside perspective, you would need absurdly more energy. The cost curve is not linear. It explodes. So here's the quiet, profound point. The universe doesn't stop us with a wall. It doesn't slap our hand away. It simply makes the price of ultimate speed so high that reality itself refuses to pay it. You can approach the limit forever, but forever isn't fast enough to outrun the galaxy. Let quote. Forget about engines for a moment. Forget about energy. Forget about relativity. Let's just talk about size. Because sometimes the problem isn't speed, it's scale. Imagine you shrink the Earth down to the size of a marble. Just a little glass marble sitting on your desk. If the Earth is that marble, the moon would be about a small bead orbiting a few inches away. That already feels spacious. Now where would the sun be? Not across the room. It would be about 100 meters away, roughly a football field's length, and it would be a large beach ball. Already, the solar system is mostly empty space. Now let's go bigger. On that same scale, where's the nearest star? Not the next house. Not the next city. Thousands of kilometers away. The gap between stars is so enormous that if you replaced the solar system with something you could hold in your hand, the next one would be on another continent. And that's just our local neighborhood. Now, stretch your imagination further. The Milky Way contains hundreds of billions of stars, and it's about 100,000 light-years across. A light-year is not a measure of time, it's a measure of distance. It's how far light travels in 1 year. And light is not slow. It circles the Earth 7 times in 1 second. So when we say the galaxy is 100,000 light-years across, what we're really saying is, even if you travel at the fastest speed nature allows, it takes 100,000 years to cross from one side to the other. That's the scale. Now here's where intuition fails us. Human beings evolved to understand meters, kilometers, maybe thousands of kilometers. We can stretch to imagine crossing oceans. We can even grasp going to the moon. But the jump from planetary distances to interstellar distances is not just a bigger number. It's a different category. Think of it like this. If walking across a room is like traveling across your city, then traveling to another star is like walking around the Earth millions of times without stopping. And crossing the galaxy is like walking around the Earth billions of times. The numbers become so large that they stop feeling real. But physics doesn't care whether the numbers feel real. Distances in space are not obstacles like mountains that you can tunnel through. They're empty, mostly vacuum. But emptiness doesn't make them small. And here's the subtle part. Even if you could travel near light speed, even if time slows down for you aboard your ship, the galaxy's size and the rest frame of the stars remains enormous. Civilizations rise and fall on time scales of thousands of years. The galaxies crossing time is 100 times that. So interstellar travel isn't just an engineering challenge. It's a civilization-scale commitment. You're not taking a trip. You're launching a lineage. And the further you want to go, the more the scale itself becomes the dominant factor. The physics of speed limits is one barrier. The physics of energy is another. But the sheer size of the Milky Way is a third quiet constraint. The universe doesn't need to trap us with force fields. It just makes the distances so vast that even at ultimate speed, the journey stretches beyond ordinary human horizons. The galaxy isn't a cage with bars, it's an ocean so large that even light needs a lifetime to cross it. All right, let's shift gears. Just suppose we solve the speed problem. Suppose we build engines powerful enough to crawl right up close to light speed. Suppose we're willing to wait thousands of years from Earth's perspective. Suppose we even build generation ships. Are we free then? Not quite. Because there's another law quietly sitting in the background, and it doesn't care about ambition. It's the second law of thermodynamics. Now that sounds technical, but the core idea is very simple. Energy spreads out. Order tends to become disorder. Useful energy turns into less useful energy. Think about your morning coffee. You pour it hot into a mug. You don't come back an hour later to find it hotter. Heat flows from hot to cold, not the other way around. The energy spreads into the room. That's entropy increasing. Now imagine a spaceship traveling between the stars. It has engines, life support systems, computers, maybe ecosystems inside. All of those systems require organized energy, low entropy energy to function. They burn fuel, produce waste heat, radiate energy away. Every single process produces entropy. On Earth we deal with this easily. We dump waste heat into the atmosphere or oceans. We grow new food using sunlight. We rely on the sun as a giant low-entropy energy source. But in deep space between stars, there is no nearby sun. It's cold, it's dark. You must carry your energy with you, or collect it from extremely sparse radiation. And here's the subtle constraint. The longer your journey, the more entropy you must manage. A trip across the galaxy isn't just about distance. It's about sustaining ordered systems, biology, machinery, information for tens of thousands of years. Every component ages. Materials fatigue, random molecular jiggling slowly degrades structure. Entropy doesn't smash things dramatically, it whispers. Metal corrodes, seals leak. Electronics accumulate tiny failures. Even DNA picks up copying errors. To fight entropy, you must constantly repair, recycle, and reorganize matter. That requires energy, and not just energy, high-quality energy. Now think about this carefully. If your journey takes 100,000 years, your ship must function longer than any civilization in recorded human history has existed. It must maintain closed ecological cycles with near perfection. Even tiny inefficiencies compound over millennia. It's like trying to keep a sandcastle perfectly shaped while waves gently lap at it. Not for an afternoon, but for geological time. The second law doesn't say it's impossible. It says the bookkeeping must close. Every correction costs something. Every repair generates more entropy that must be exported as heat. And exporting heat in deep space is slow. Radiation is your only option. You need large radiators. You need careful temperature control. The ship becomes a delicate thermodynamic machine. Now step back. Interstellar travel isn't just a matter of can we go fast enough? It's can we maintain order long enough? Speed limits constrain motion. Energy requirements constrain acceleration. But entropy constrains duration. And here's the deeper insight. The second law is statistical. It arises because there are vastly more disordered arrangements of matter than ordered ones. It's not a moral rule. It's a numbers rule. Nature simply prefers the more probable configurations. So if you want to maintain a tiny bubble of order, a living civilization inside a cold, expanding universe for immense spans of time, you're swimming against an overwhelming statistical current. That current doesn't forbid exploration, but it raises the cost. And when you combine immense distances, near-light speed, staggering energy demands, and relentless entropy, you begin to see that the galaxy doesn't need prison bars. The laws of thermodynamics are patient enough. They just wait. Now we arrive at the most tempting escape hatch of all. Whenever physics tells us you can't go faster than light, someone raises a hand and says, fine, we won't go through space faster than light, we'll bend space instead. Wormholes, warp drives, shortcuts through space-time. It sounds clever, and it is clever. The equations of general relativity, our best theory of gravity, actually allow strange geometries. If mass and energy can curve space-time, then in principle space-time can be curved into tunnels. Two distant regions might be connected by a shorter path, like folding a sheet of paper so two dots touch. From the outside, it looks like magic. Step into one mouth of a wormhole, step out somewhere thousands of light years away. No speeding required. So why don't we just build one? Here's where the quiet, careful reasoning begins. First, the mathematics allows these structures, but mathematics is permissive. Nature is selective. Just because an equation has a solution doesn't mean the universe can actually realize it. To keep a wormhole open, calculations suggest you would need something called negative energy, not just low energy, but energy with properties that violate the usual conditions matter obeys. We do see tiny effects like this in quantum physics, but only in microscopic fleeting amounts. Nothing remotely large enough to hold open a tunnel big enough for a spaceship, so already we're stretching the known laws. But suppose you could stabilize one. There's a deeper issue. Causality. Cause comes before effect. You flip a switch, then the light turns on. That ordering of events is woven into relativity itself. It's what keeps the universe logically consistent. If you can travel faster than light, even indirectly through a shortcut, you can arrange situations where, from some observer's perspective, the effect happens before the cause. Signals could loop back in time. You could, in principle, send information to your own past. Now, this isn't science fiction drama. It's a direct consequence of how relativity handles time and motion. Once faster-than-light communication is allowed, the neat structure that kept cause safely before effect begins to unravel, and physics seems deeply allergic to that unraveling. Whenever we try to design these faster-than-light schemes, paradoxes creep in. The equations don't explode, but they start demanding increasingly exotic, unstable conditions, infinite energies, unphysical matter, perfectly arranged initial states that seem statistically impossible. It's as if the universe is saying you may explore the boundaries, but consistency comes first. There's even a hypothesis, not proven but suggestive, that the laws of physics conspire to prevent time machines from forming, that quantum effects would destabilize any space-time geometry that threatens causality on a large scale. Now notice what's happening. It's not that someone wrote a cosmic rule, no intergalactic travel allowed. It's subtler. The same structure that gives us reliable cause and effect, the same geometry that keeps the speed of light invariant, also blocks the shortcuts. You can curve spacetime. We do it every time we put mass somewhere, but to curve it enough to cheat the light speed limit may require ingredients the universe simply doesn't provide in usable quantities. So in the end, the jailer isn't distance alone, it isn't energy alone, it isn't entropy alone, it's consistency. The laws of physics fit together like gears in a watch. If you force one gear, say faster than light travel, the others grind. Causality, energy conditions, quantum stability, and the watch resists, not violently, just inevitably. The galaxy may not have walls, but space-time has rules, and those rules may be the deepest boundary of all dot. So where does all of this leave us? We started with a simple question, asterisk, what traps us in the Milky Way? And the answer, strangely enough, isn't a single wall or a single law. It's a web of them. First, the structure of space-time itself sets a speed limit, not as a punishment, but as a built-in feature of reality. The speed of light isn't just fast, it's woven into how space and time fit together. Try to outrun it and time bends, inertia grows, and the energy cost skyrockets toward infinity. Then we looked at the sheer scale of the galaxy. Even if you could travel almost as fast as light, the Milky Way is so vast that crossing it takes longer than civilizations typically survive. The distances are not dramatic obstacles, they're just unimaginably large. Add to that the second law of thermodynamics. Entropy quietly accumulates, machines degrade, energy spreads out, keeping a fragile bubble of order alive for tens of thousands of years in deep space isn't forbidden, but it's brutally expensive in energy and precision. And finally, when we try to cheat, bending space-time, tunneling through wormholes, inventing shortcuts, we run into something even deeper, causality. The universe guards consistency. Faster than light travel isn't just about speed, it threatens the very logic of cause and effect. Put all of that together, and you begin to see the picture. The Milky Way may not be a prison with iron bars. It's more like a beautifully constructed maze made of geometry, energy, probability, and time, and every path outward runs straight through the deepest principles of physics. Now here's the important part. This isn't a story about hopelessness. It's a story about understanding the rules of the game we're playing. Because once you see the constraints clearly, really see them, you stop fantasizing about breaking physics and you start asking better questions. How far can we go? How long can we endure? What does exploration look like within the laws, not against them? That's where real discovery begins. If you enjoyed thinking this way, not just learning facts, but carefully following the logic of the universe, then subscribe to the channel. We'll keep pulling apart big cosmic questions with clarity, curiosity, and respect for your intelligence. Because the more honestly we understand the limits, the more astonishing the universe becomes. Thanks so much for sticking with me and exploring this cosmic puzzle together. I love thinking about these things, the strange, subtle rules that shape our universe. And I hope you enjoyed puzzling through them too. Keep asking questions, stay curious, and never be afraid to follow the logic wherever it leads. I'll see you in the next video.